start. So my presentation is called the facility location problem with freight distribution to support freight efficient land use. So the outline of the presentation of today, first I'm going just to give like a small motivation, then I'm going to start talking about the goals and the objectives that I have, the problem description and the mathematical formulation that I did for this research. I'm going to present a small and a large test case, and lastly some key insights from this test case. So as a motivation, well, first I want to highlight the importance of supply chain model economies. Freight transportation and logistics in general, they are key elements in the growth and sustainability of any country, region, city, town. In the US, 80% of the US cargo is transported between the top 100 metro areas. The logistics account for 8% of the GDP of the US, which is equivalent to $1.6 trillion per year. And more than 13 million people are employed in transportation or transportation-related occupation. It's almost 9% of the available jobs in the US. Freight transportation actually, I think the battery died. Freight transportation, it acts as a market facilitator by connecting key supply and demand on rapidly changing markets. However, by doing so, it is one of the industry sectors that produce the most greenhouse gases emissions. So in the US, it's the industry sector that produces almost 30% of the greenhouse gases emission, and out of that, 81% of it comes from light, medium, and heavy-duty vehicles. Something as well that is important to highlight is this interaction that is intertwined between the land use and the transportation systems. So usually cities, they have these zoning systems that in essence they determine where activities can locate and operate. So in essence, for instance, you would see how residential and commercial establishments are located nearby to promote a synergy between those type of land uses. And actually planners, they have to face this daunting question, that is, how are we going to organize the territory? When I was a kid, I was kind of a nerd, and I liked this game called Sims. I don't know if you ever played it, but in essence what you had to do is how are you going to organize the city, what you wanted to do. Of course, I didn't know back then, but we wanted to maximize welfare of society. And so we had to put, like, where are we going to put the buildings, where are we going to put the factories, where are we going to put the jobs. And as time went by, I started to realize how this game actually looked more like a chessboard, in which we had to be way more strategical, because depending on how we put the different types of land use, they are going to have a huge impact on the urban economy. So when I was doing my PhD back at RPI, we were working on a project for the National Cooperative Highway Research Program, and this project, it had some concept that it was new back then, and it was really interesting for me. That actually it was one of the main motivators for my dissertation. That is the concept of freight efficient land use. So a freight efficient land use is an aspirational concept in which what we want to do is to hopefully get land use patterns that minimize the social cost associated with both supply chains and economic activities that consume and produce goods at all stages of production and consumption. By social cost, I mean the definition of Pico on 1910, that the social cost in essence is the summation of private cost plus externalities. So to illustrate this concept, let's imagine that we are one of these urban planners, and we are given three choices on where we can locate our distribution center. The first option is, well, first let me explain the image that you see here. So imagine that on the top left you have a regional distribution center. How it usually goes is from the regional distribution center, it would go to a urban distribution center. And then from the urban distribution center, it will go to this gray area that we could call it maybe the central business district that any city would have. That is one of, well, usually is the largest attractor of cargo. So the first option that they gave to us, it was, well, it's on the outskirts of the urban distribution center, but it has like the truck that usually does this type of distribution from the regional distribution center to the urban distribution center. It's the long haul semi-trailer, 53-foot long, that you would see on the highway. And from the urban distribution center to the central business district is the smaller size vehicles that they are the ones that usually fulfill the shorter delivery tours. The second option that we would have is that now the urban distribution center is located in the northern part of the urban area, Again, we would have the same concept of from regional distribution center to urban distribution center, the long haul, and from urban distribution center to the central business district, the smaller size vehicles. And lastly, we have this option that is the location C, that kind of the urban distribution center is located in a middle point in which it's like in the urban center. And if I could ask any of you, I don't know if you're shy to participate, but among these three options, which one, for instance, Alec, do you think would be the best one?
Probably B or C.
Exactly, because I mean, we could argue it's option C, because for instance, in option C, then we would have shorter distribution routes from the urban distribution center to the center of the city. So, like for instance, in this example, and what I want to highlight is the importance of where we locate the distribution center is going to have on the subsequent distribution routes. So the goal of my research, it was in essence to enrich analytical techniques for this freight efficient land use policy and planning. And to do so, I had several objectives. So the first one is I wanted to develop a mathematical model that it was capable of identifying where were we going to locate distribution centers by minimizing the total social cost associated with facilities that generated vehicle tours. As I mentioned, social cost for me it was the summation of private cost plus externalities. I wanted to consider explicitly the unique features of vehicle tours because as many of you might be aware, when we start modeling vehicle tours, they are quite different than the traditional type of trips that is a unique origin and a unique destination. So for instance, the typical gravity model, it wouldn't work when you are modeling vehicle tours, but when we're doing a unique origin and a unique destination, it would work. And I wanted to capture as well these interconnections between location decisions, demand patterns, vehicle tours, and the associated externalities. So now talking about the problem description and the model formulation, first I wanted to present it in a schematic way. So imagine that we have a city, that this city is like in this rectangle. On the left here we have something called the gateway. So the gateway could be a maritime port, an airport, or wherever the cargo is arriving. And then we know that we're going to have a long haul trip to the distribution center that is located 10 miles away. And then we know that from the distribution center, it would go to both establishments and households that require the cargo and the final consumers. And smaller size vehicles would do those tours. If we compute the vehicles miles traveled of this simple schematic, it would be 150 miles. However, if we move this distribution center to be 20 miles, so then it would be located closer to establishment and households, and we compute again the vehicles miles stored, then there is a reduction of almost like 40%. So what I want to show in this example is how the location of this distribution center, it impacts on the subsequent tours that we are going to have, and as well, it impacts the efficiency of the supply chain overall. So what I did, it was a bi-level problem in which I have a facility location problem, and embedded, I have a freight tour distribution model. So now, talking about the mathematical formulation, I'm not going to enter into many details, but I'm going to explain both the set, parameters, variables, and then the problem itself that I modeled. So regarding set, I have, I'm doing a discrete facility location problem, so I had to have a set of all the potential locations in which a logistics center could be located. I'm modeling several industry sectors. As well, within my model, I have said that it kind of have all the possible tours that could be done when we are distributing. And then what the model does is that it assigns the freight tours into those set of possible tours. Then, each tour is a node sequence of order nodes visit by a vehicle tour. And I have a subset of links that, well, I'm going to explain it later on, but since I'm modeling using a bi-level problem, then I should have a linking constraint that connects my lower level problem with my upper level problem. Regarding parameters, well, I have the typical things that you would have. So it's total number of nodes, links in the network. You have travel times for each link. Regarding variables, for instance, I have binary variables that indicate if a facility is open at a certain location. I have the tour that is going to be assigned to each of the distribution. I have as well binary variables that indicate if a link or a node is being used in the tour. And now talking about the problem, so as I mentioned, it is a bi-level problem. So by definition, a bi-level problem you could think it as two optimization problems that are one embedded into the other. So in the upper level problem, my objective function is what you have in this square now. So the first component of this objective function, in essence, is just the fixed cost of opening a facility at a certain location. The second component that you would have is actually the operational cost that it would be when the tours are going to, like the generalized cost of distributing the goods. So by generalized cost, I mean the total travel time, I mean the travel time cost, the monetary cost, and the cost of tolls, if there are so. And lastly, this third component, it would be the evaluation of emissions. Because as I mentioned, one in my objectives, what I wanted to do is to minimize the social cost. The social cost is the summation of private cost plus externalities. And as we know, all the when any delivery tour, it is transversing and it's doing certain vehicles miles traveled, and these vehicles miles traveled we can then translate it to emissions. And with valuation techniques, then we can add a monetary value to those to those emissions that we have. Regarding the constraints in the upper level problem, we have the typical that at least one facility is being selected and the integer variable. And regarding the lower level problem, then I want to explain first the concept of entropy maximization. I don't know if some of you may be aware of it, but in case not, at least I'm going to explain it briefly. So entropy maximization problem is actually a dual of maximum likelihood. So then you could imagine it that by doing entropy maximization, you would be able to find the most likely state of whatever you're modeling. So it was developed by Wilson in 1970, and it assumes that any given probability function in any state is equally probable. And in this case of urban freight, it means that we could see a freight vehicle tour has the same probability of being observed. There are three possible states that can be found on urban freight. So we have a microstate, that is the tour of a single commercial vehicle starting and ending at a home base. We have a mesostate, that is the total number of commercial vehicles following a specific tour. And lastly, we have a macrostate, that kind of is the total number of trips produced and attracted in the network. So you could imagine it more like on a city scale one. And what we intend to do is to find the most likely mesostate given some certain constraints into the model. As I mentioned, this entropy maximization model, well, it was developed by Wilson in the 1970s, but it has been used for several authors to model tour distribution. The typical formulation is what you find here. Then what we do is that, for easiness, what we do is that we maximize the logarithm of W, since it's a monotonic function, and then we can use a Stirling short approximation to jump from the first equation. Let me put here, let me use the laser, that's the case. To jump here, and then since we know the total number of trips is a constant, then we can maximize it's just logarithm of W prime. That in essence what we want to do is to be subject to some macro state constraint to estimate the most likely mesostate. So what does this mean in my model? Well, then this is the lower level part of my problem. What I do have is the entropy maximization here as the objective, and then I have 8 set of constraints. The first 4 are the ones that I call some urban freight constraints, that in essence what they do is that they ensure that the total freight trip attracted in each zone of the model is satisfied. Then as well I have ways of how I can capture the total cost, the total distance, and the total travel time in the network. I have the typical non-negativity and binary variable constraints. And as I mentioned, since I'm going to model a bi-level problem, then this bi-level problem should have a constraint that kind of connects my upper level with my lower level problem. That one is the linking constraint that you are seeing in that black box. And the rationality behind this linking constraint actually is quite simple. That is, imagine on this example that we have 3 possible locations where we are going to select our distribution center. Location 2 is selected, then we should ensure that from location 2, all the subsequent tours have to be tied to the dispatcher location. So in essence, if location 2 was selected, then all the tours should have as origin and as at the end of the tour, the destination location 2. So this is how actually my bi-level problem looks like. The traditional methodology how you solve any bi-level problem is that the lower level problem you use the Karush-Tucker condition, so then you would have to do primary feasibility, dual feasibility, and complementary slackness to compact your lower level problem into the upper level problem. However, there is this issue that my problem has binary variables. So when you have a binary variable, then you cannot do dual feasibility because integer variables do not have a dual. So the traditional bi-level methods, they fail to solve integer problems. So what we can do is actually we can use sensible upper bound, and by using the sensible upper bound, then we would have a binding constraint, and we can compact my bi-level problem into a single level problem. So what does my model do? It minimizes the social cost, and it's a way how we can distribute freight tour flows. So this is my base model. I did a small variation of this base model that I'm not going to explain in further detail, but in essence what I did was I used the methodology of shadow price in order to reevaluate how we were going to measure the externalities. And the reason why I did it was because, as you will see in a couple of slides, I developed my model for New York City. And in New York City, it has been built in of a large income inequality, after, for instance, 1960s. And just to give you, for instance, a fact is that the children in the Bronx, they have higher asthma morbidity than any other children in the US. So an additional vehicle might travel, for instance, in the Bronx. It shouldn't be evaluated the same as a vehicle might travel in Manhattan. So that was the reason why, or my main motivation why I wanted to do variation in this model that I did. So now, presenting some small test case. This small test case I just did it was for a proof of principle. So I divided New York City into 13 gigantic zones. My model, as you would imagine, it requires a lot of inputs. So for instance, for the location cost, I used the proxy that 1 metric ton would require 25 square meters. And then, for instance, for commercial deliveries, there were some models already developed in the US, actually developed by my advisor, that he was able to compute the total freight attracted in his case it was by zip codes, but then I just aggregated it into the zones of my model. And regarding e-commerce deliveries, the National Household Travel Survey in the US, it gives you a ratio of number of e-commerce deliveries by person. It's around 0.12 in New York City. But I needed to translate this number of e-commerce deliveries into a weight measurement. So by using the results of a survey that it was conducted to more than 100 shippers in France, I was able to obtain a discrete weight distribution of parcels. So, for instance, almost 66% of all the parcels that are being distributed is less than 1 kilogram. Regarding the generalized cost parameters, as I told you, one component of my objective function is the operational cost, and the operational cost in my case is the generalized cost. So I have the cost per minute, cost per mile, and the toll rate, given the fact that I model New York City, so once you're going to enter to the city, you have to pay a toll that is $38. Regarding emissions, I use 4 different pollutants, that it was carbon monoxide, carbon dioxide, nitric oxygen, and PM 2.5. And, I obtained distance and travel time matrices using Google Maps. And the result of this, let's say, proof of principle model. They were kind of what it was expected. So in essence, what I obtained, it was the less expensive location costs. They were associated with more externalities. So what this means is, for instance, that areas that are located outside of Manhattan, that Manhattan is the main core of attraction, then it would produce more externalities because, of course, then vehicles would have to travel like a larger distance, and as well as going to then generate more impacts in the network. And I found how the area of south of Queens. Then let me go back to the map. So the main areas that attract the most carbon in New York City is these three, that is Manhattan. Then you have Brooklyn here, and then you have Queens. These three areas, among the three of them, account for 70% of all the freight trip attracted in New York City metropolitan statistical area. And I found how this area, that is the south of Queens, could be like an optimal place where we could start placing distribution centers, because they would be able to fulfill in a more expedited way, like the deliveries that are required now in New York City. So these are the results of my proof of principle model, but of course I needed to scale up this problem in order to be able to have a larger insight. So what I did, it was, of course, I changed the zoning. So as you will see in the next couple of slides, I scaled up from 13 zones to 105 zones in my model. I modeled different industry sectors, but for the sake of time, I'm just going to present one of them, that is actually the combination of manufacturing, retail, and accommodation and food services. And the reason why I selected these three industry sectors is because when you sum those three industry sectors, they account for more than 50% of all the freight trips attracted in New York City. So if you're able to model these three of them, then you would already be having some like insightful, like you could have some valid insights about like the freight distribution in the city. As well, I wanted to do, and I'm going to show like a sensitivity analysis regarding location cost, and well, I'm going to present the results. So, as I was mentioning, differences about the zoning, I scale up the problem to 13 zones to 105. Something as well that I did, it was on my previous model, I used exact solution. So I used ample in order to solve my model, but well, in this case, it was not feasible because my problem is an hard problem, so I had to use a methodistic. So one thing that, given the size, given the fact that I scaled up my problem, then the tours, for instance, that it would be a set into my model. If I use a complete enumeration technique, that it would be a power set functions, they increase to the power of 2 to the n. So given the fact that I have 105 zones, then it would give me a radical number of possible options, which in essence it was not feasible. So I did a discrete probability of freight trip attraction, just ensuring that each location would have at least 100 different round-trip tour sequences, and then it would assign the tour flow. Each industry sector had different typical number of stops in the tour. As I was mentioning, I used genetic algorithms as a methodistic to solve my problem because that exact solution, it was unfeasible. And regarding the results. So if we see this map is the one of distance, there are three main areas that would minimize the total distance traveled in the system. So of course you have Manhattan, that is this area around here. We have the northeastern part of Queens and the north of Brooklyn. And you have this area in New Jersey, which is interesting because it's the area right in front of the Lincoln Tunnel. So it has direct connectivity to three of the main sources of freight trip attractors. And it's, of course, in terms of location cost, it's way cheaper than Manhattan. If we see a similar map, but just regarding the travel time, it's a similar pattern. Of course, we have Manhattan, we have the north of Brooklyn. Actually, here it's connected to the Brooklyn Bridge. Here we have the northern part of Queens. I'm going to here. Here, this area is called Richmond Hill and Kew Garden in Queens. This area is quite particular because it's in an intersection between two of the major highways in New York City. So you could imagine it's like a T, that it transverses, this is Queens, this is Brooklyn, so it goes from east to west and north to south, so it has a really large connectivity area. And you have this area in New Jersey that is in the top, that is actually the area that is right in front of the George Washington Bridge. So then you would have, again, like direct connectivity to the northern part of Manhattan or the Bronx. As I told you, my model, what it does is minimizes the social cost, but the social cost is the combination between the private cost and the externalities. And I want to point out with these maps is just like that they are directly interconnected, but they are completely opposite in the sense that, of course, like building a distribution center in Manhattan, it would be optimal for society because then you would have shorter delivery tours. But by doing so, just like the location cost would be prohibitively high. And it would be like too expensive. So what my model did, it was like a combination of these two. In order to get the social cost, and like the social cost, there are 4 areas. So the first one, that is here in the north of Manhattan, like the northeast. Actually, it's where the location cost is the cheaper in Manhattan. It's called East Harlem. As well, there is a small island, I'm going to point it out here with the red dot, that is called Roosevelt Island. So that Roosevelt Island is kind of like government owned, and well, it's like a perfect location to connect like between Manhattan and Queens. You have as well the northern part of Queens. You have this area that it was the one that I told you that it's right besides the like 2 of the major highways that connect east to west and north to south, Brooklyn and Queens. And you have this area here in the south that is, funny enough, it's called East New York, but it's located in Brooklyn. And as well, like in that area, several of the large retailers such as Amazon or Best Buy are starting to build their distribution centers to fulfill those expedited deliveries. In essence, that they would, in New York City, they are promising like even 1-day delivery or same-day delivery. So, the only way how they can fulfill that promise is by having distribution center close to where the cargo is needed. So regarding the model, I also did the sensitivity analysis. And in essence, what I want to point out is if land was free, just assuming, of course, like if we built a distribution center in Manhattan or the western part of Queens, it would be great. If it's 30% of the cost, then just because the cost of land is so prohibitive, then the optimal it's like shifted to the part of Queens, and then for 70 and 100%, then like you saw the 4 different like options. So some key insights of these test cases. So in essence, what my model did, it was to highlight how there is this trade-off in order to be close to the main attractors of cargo, and as well, there is this trade-off with the location cost. Something that I didn't show here just for the sake of time, but it was that when I did my models using the second model that reevaluated the externalities, some vulnerable areas were protected from being selected optimally. So for instance, I believe it was in the manufacturing sector, there was, the result of my model, it was that building a distribution center in the Bronx would be optimal. But for instance, the area of the Bronx is the one that, they have been suffering the most externalities that the transportation sector have. And for instance, it's the lowest, is the borough that has the lowest income, and actually is where most of the people in New York City live. So as I was saying, an additional vehicle might travel in the Bronx, it might not be like the best option. And as well, when I was doing the sensitivity analysis, like I clearly saw how I believe there is a non-export path on like land use policies that we could use, either rezoning, pricing incentives, or taxation in order to bring, again, the logistic facilities back again into the urban core. As I was saying, like there is also this environmental justice model. It shifted the location, like for instance, from the Bronx or certain areas in Queens to New Jersey or Staten Island. And I believe actually what I learned after like doing this project, like my dissertation, it was that I believe it's critical to understand this interplay between supply chain efficiency, land use ordinances, and trade activity if we want to like consider holistically like planning in general. If we want to have like an efficient and sustainable city, then freight should be like considered as well, and especially like this interconnection that it has with land uses. Okay, that's my presentation. So if you have any questions, I'll be happy to answer.